Welcome back, everybody. Thank you. We're going to go into a little bit of a science chat, and for those who may be streaming, I'll just mention the email question place that you can pose a question if you like. Again, the address is corrim@mmc.org. We've just swapped Dr. Sears and Dr. Zuckerman. They were really anxious that we weren't going alphabetically by their last names. So we thought we'd just flip that around. No, they'll explain kind of why, I think. But what's Dr. Sears, Ted Sears, is up first, and he's going to be really drilling into the newest drug that Emily was talking a bit about, Orkambi and the Kalydeco stuff. So we'll get a good dose of that. A lot of people are curious about this, and this is what we'll cover first. And then Jonathan Zuckerman is going to come up and talk about genes to dreams, but give a bit more of a contextual view of what's kind of going on in the science space. So thank you both for coming up, and I'll let you pass off directly when you're done.
Well, I'd like to thank the family group for inviting us here today. We're always excited to come talk. Jonathan and I decided to flip-flop our programs a little bit just because actually I'm going to be starting with a little bit of data about Orkambi and what the sort of next things that are coming down the pike that are sort of Orkambi and F508del related, and Jonathan's going to sort of take us out to the farthest frontiers of science and the stuff that's coming next, and so it makes a little more logical sense this way, hopefully.
Let's see if the mouse works from there.
Yeah, we can try that. So, as I said, I'm going to be talking a little bit about F508del and what's coming down the pike in terms of new therapies. Let's see if, so I do have a couple potentially relevant disclosures. I am the site PI for the SNOW 6 trial, which we will be mentioning today. As well, and I do participate in a number of other trials through the Cystic Fibrosis Foundation Therapeutic Development Network. And we are a site here in Maine. Actually, all of the doctors who you see in Maine are involved in research through the TDN. And we're really excited that Emily gave us a shout out there. We agree 100% that the future of this disease lies in the research and the new things that are coming down the pike, which are hopefully going to start having broader and broader applicability to every patient with CF. And although I am going to talk about F508del today because it's a really common mutation, we will be, a lot of this stuff is, as I said, is spreading out to everyone. So starting off with a little bit of background about F508del, why do we care about it? Why do we talk about it? It is the single most common mutation, and as Emily was alluding to earlier, this is becoming a genetic disease. As a CF doctor, the first question I ask when I meet a new patient is what's their mutation, because that really defines some of the therapies that we use already. And so F508del is at least 86% of the U.S. population thereabouts have one copy, and 47% of patients in the U.S. have two copies of F508del. And so it is sort of the gorilla in the room when we're talking about the genetics of CF. You don't need to worry too much. The reason it's called F508del is because it deletes the 508th amino acid in the protein. And for the science geeks in the room, this is how we break down how mutations work in CF. And so there's the basic classification. Obviously, everyone has DNA in the nucleus of the cell, and that's actually where the mutation lives. But how the DNA changes affect the function of the protein is really where this disease comes from. And so that we can talk about different types of mutations. This is F508del is what we call a class 2 mutation, which is to say that you have DNA gets made into RNA in the nucleus, and then it comes out. And your cell has little factories that are supposed to turn that transcript into the protein, into CFTR. And the problem with F508del is partially that the factory does not work, that when the cell tries to make the protein, it fails. And then partially that if it does somehow manage to successfully make the protein, when it gets up to the cell surface, and this is a little diagram showing the protein to the cell surface, it doesn't work very well. And so we call that a combined class 2 and class 3 mutation, which is to say there's a misfolding component and there's also a decreased function, as well as some increased turnover. So I'm going to start off with talking a little bit about Orkambi, because Orkambi is, as you guys all know, the really exciting new drug that we're using for patients with F508del who have 2 copies of the genes, so-called homozygotes, which is they have 2 copies of the same gene. And it's sort of the framework around which a lot of the new drugs coming down the pike are built. So this is actually meant to represent that process I was just talking about, where your cell is going to try and make a CFTR protein. As we're going to see here comes a little ribosome that's trying to make the protein. And as the protein is being made, we see this little purple thing coming in and binding to that protein. That is lumacaftor, which is one of the 2 drugs that's in Orkambi. And the point of lumacaftor is to help this protein fold correctly, because as we said, the problem with F508del is when your body tries to make it, it doesn't fold right. And this protein sort of fits in like a little bit of a key in a lock and forces that protein to fold more correctly than it would otherwise. So we see suddenly that sort of, and suddenly we see a completed protein suddenly being made, whereas previously the body was not able to make that protein. And then the second step is that those completed proteins need to travel across the cell from where they're made out to the surface of the cell, which is where all the action happens. And so here you can see a bunch of those proteins jumping onto the surface of the cell, which is the way they're supposed to. So lumacaftor has done the first part. Now the problem is that even if we get this in there, you can see the lumacaftor still stuck to that protein. Doesn't actually necessarily work that way, but for the graphics point of view, you can still see it's there. But you'll notice there's these little green things, and these little green things are the chloride ions. And we know that CFTR, one of its big functions is to be a chloride channel. And you'll notice there's a lot of chloride ions down here, and not very many are making it through the protein. Okay, so that's the second part of the problem with F508del mutation, is that it's a gating mutation, and it doesn't want to, the protein, even when it gets to the cell surface, doesn't want to open, it doesn't want to let those chloride ions out. So now, suddenly we see a second molecule come in. Ta-da, and that is ivacaftor. That is what is sold as Kalydeco, but is also part of Orkambi. And when the Kalydeco hits the mature protein at the cell surface, it suddenly opens it, and a lot more chloride ions can go through this protein. And so this is the correct. This is sort of the new thinking in how are we going to rescue CFTR and actually deal with the molecular basis of the disease, is cocktails of drugs. One drug that does one thing, helps the protein fold, another drug that helps open the protein. Other drugs that may have other effects down the line. And that's sort of the initial success of Orkambi is sort of really pushed forward this whole idea of how do we fix the basic defect in CF. Okay. The other thing I'll just point out, if you guys have questions as we go along, please feel free to ask them. I prefer audience participation. I'm trying to make this as clear as possible. If I lapse into science speak, please stop and be like, hey, that doesn't make any sense.
Are you going to explain why it's a problem for people with CF when those proteins don't do what they're supposed to?
Okay, I can go into that. I didn't put a couple of slides in that specifically. I was trying to keep this tight, but the real problem being that we just talked about how CFTR's job is to allow chloride ions to exit your cells in the airway, and that actually turns out to be really important for maintaining the proper amount of fluid and water in the airway and in the mucus in the airway. And when you don't allow chloride ions out, there's not enough water in that mucus. You end up with thick mucus. And then thick mucus gets infected, is hard to cough out, and over time causes damage and destruction to the lungs. And you get this sort of vicious cycle of infection and inflammation. But the root cause, we think, and there's actually still debate about this, honestly, but the current orthodoxy is that if we can open up and make CFTR work, we will loosen mucus up and make it thinner, make it easier to cough out, and decrease the amount of infection and inflammation and lung destruction that happens over time. So this is the data that we have from Orkambi, which, as I said, is lumacaftor and ivacaftor, these 2 drugs. Lumacaftor, the folding corrector, ivacaftor, opening the channel. But it really only works for patients who have 2 copies of the F508del gene. So you have to be one of these people who's a homozygote. This is data from the New England Journal article published last year, which is sort of, and you can see 2 things. Number one is the change from baseline in percent predicted FEV1 for patients who are put on our combi is pretty modest, okay? This is 0, this is 2, this is 4. So we're talking about a 2 to 3% improvement in their FEV1, which is not, it's, well, don't get me wrong, any improvement in your FEV1 is good improvement in your FEV1, but it's not, it's not knocking it out of the park, and it's not the size of improvement that we saw with ivacaftor in patients who have G551D. They got a 10% improvement on average in their lung function with the addition of ivacaftor. So this is a much more modest effect. The real benefit from our point of view, or the biggest benefit from our point of view, is probably in the second graph here, which is pulmonary exacerbations in patients who are on our combi. And so here are patients who are on placebo, and the patients who were on the higher dose of ivacaftor, the twice-a-day dose, which is the dose that was actually approved and is used, had about a 60% drop in events leading to hospitalization and a 50% drop in the number of times they needed IV antibiotics. Now that's huge, right? Like that, going down from being admitted 4 times a year to being admitted twice a year makes a big difference in your quality of life. And so really, the FEV1, yeah, it's good. I'll take it. Don't get me wrong. I'll take anything I can get. But it's probably the exacerbations are the thing. But in the final analysis, this wasn't we didn't knock it out of the park here. Okay, we got a solid single or maybe a double. So this is another thing that Emily had mentioned earlier, which is sweat chloride values. Why did she taste less salt on her skin when she was on these drugs? Okay, so across the bottom here are different levels of mutation, more or less, in patients who have CF. So controls would be people who do not have CF, and they normally have a sweat chloride of about 20. Okay, patients who have one abnormal gene and one normal gene, incidental heterozygotes, occasionally have slightly elevated sweat chlorides, but it's still pretty low. There are actually people out there who actually have 2 CF mutations, but they're pretty mild. They have a sweat chloride that's in the 50s. They don't get lung disease. They don't get pancreatic disease. Actually, we find them sometimes because men don't have vas deferens, which is the tube that connects the testis to the penis. So they get found incidentally, they can't have kids, and someone, oh my gosh, he doesn't have vas deferens, they check, oh, he's got CF, except his sweat chloride's so low he never had any symptoms. When we start getting sweat chlorides in the 60 to 80 range, we get patients with a quote-unquote milder form of CF. Those are usually patients who are pancreatic sufficient but have lung disease. And for the patients who have really high sweat chlorides, they're up at 100, they are often pancreatic insufficient patients with CF. And this is broad strokes, and your mileage may vary, and the exact sweat chloride that any individual patient has and their exact symptoms don't correlate incredibly tightly. So you don't all need to go home and check the sweat chloride results tonight.
But actually, just to make sure I understand,
yep.
508 is severe.
508 is severe. We'll get to that soon. But most patients with that 508 del who are homozygotes are up here in around 100 or 110 or 120. They're way, way up there. Okay, so what happens when we add our combi? As I mentioned, there we are. It's a modest improvement, right? We actually saw a negative 10, a drop of 10 in the sweat chloride with the addition of our combi. If you compare that to Kalydeco, which is the drug that Emily's on, she got a 50-point drop in her sweat chloride on average. This is pooled data. 50-point drop in sweat chloride for patients who are on Kalydeco. Okay, that, as you can see, could take someone who's in the severe range of sweat chloride and potentially bring them down into the sort of asymptomatic range. And that's sort of the cool, this is like the oh my god moment with Kalydeco. Orkambi, once again, good, definitely better than anything else. I mean, there's no drug like it out there, right? But we're just doing a totally different magnitude of effect. And so the real goal is, how do we make this bigger, right? How do we get a 20 or a 30 or a 40 for patients with F508 del as opposed to the negative 10? And there's a bunch of different areas where we're going with this. One idea that I'm going to talk about is what are called GNSO drugs. GNSO, and this is once again, dip into basic science here. Don't worry too much about the details. Is an enzyme that affects nitric oxide, and it turns out nitric oxide is a really important chemical inside the cell for all kinds of different functions. It does regulate CFTR. It also regulates how much your bronchi squeeze down, and when you have, when you're coughing and your bronchi are really squeezed down, there's some NO effect in there. And so it turns out that we can manipulate another enzyme that affects the GSNO, GSNO reductase. And these pictures down here just actually prove that there is actually a fair amount of GNSO reductase floating around inside the cells of patients with CF. It turns out that if you inhibit this GSNOR enzyme and thus increase actually the amount of GSNO, we don't need to go in there, you change CFTR maturation and you help the cell produce more CFTR, which is similar to what we're trying to do with Lumicaftor, right? We're trying to help the cell produce CFTR. So right here, if you have normal GSNOR, you produce an F508del CFTR. So these are cells. This is the basic science. You're playing with cells in the lab. If you have normal amounts of GSNOR, you produce very little CFTR, which we know we're raised with F508del. If we inhibit GSNOR, we start to see some amounts of immature and mature CFTR being produced. So this strategy of trying to inhibit this enzyme does seem to help the cell produce more CFTR totally differently than Lumicaftor does.
Where is this research going on, and is this U.S. or UK or?
So we'll talk about this. This actually, a lot of this stuff is that we're coming to sort of where the trial, there's actually an ongoing trial here in the U.S. Here in Maine Medical Center of a drug that does this, and that's one of the reasons I'm talking about it, because it's in phase 2, and we are enrolling patients right now to try this drug. GNSOR seems to also increases cell surface CFTR. So not only does the cell produce more of the protein, but it actually gets to the cell surface. Not as dramatic, I'll be honest, and you don't need to get into the total details here, but N1975 is a drug like Lumicaftor, which helps the cells make CFTR. And if you give them nothing, they don't make much CFTR. If you give them a corrector, they make more. But if you give them the corrector and something that inhibits this GSNOR enzyme, it makes even more. So it seems to add on, GNSOR seems to add on or boost the effect of correctors by a different mechanism. This is N9115 is actually a candidate drug, a molecule that's in development, and as I said, in current clinical trials. And this is what we think it does inside the cell. We think that you don't need to worry about the little H's, but the one thing it does is it decreases the amount of CFTR degradation, which is to say, increases the amount of CFTR being produced in the cell. There's another corrector that binds and helps the folding. It gets to the cell surface, and then once it gets to the surface, it turns out that, which I didn't really get into, but it also appears that N9115 and this GSNOR reductase helps stabilize the stuff at the cell surface, stabilize the CFTR, and decrease the degradation of it. And so that you have the potential to rescue more CFTR, get it to the cell surface, have it stay at the cell surface longer. All of which you would think would boost the effect of corrector molecules, boost the effect of drugs like Orkambi. So, actually, and as I mentioned, I am actually the site PI for this study. We are currently trialing this drug with the goal of seeing if you add this to patients who are already on Orkambi, does the Orkambi work better? Do they get a bigger benefit from Orkambi by adding a booster drug, more or less, to it? We are, so this is a phase 2 trial. We're really looking at safety still. We are starting to look at effects on lung function. We've actually, we are enrolling patients right now across the nation into this trial, and we'll see. We don't know the answer. It works great in a test tube. I've shown you some basic test tube data. The real question is, what happens when you start giving it to patients, and that's what we're trying to find out right now.
Might it be pill or inhaled or?
Currently,